This video is going to walk you through our new bomb calorimeter. So we've got the insulated container here. Inside the insulated container, we have the water drum. This is the bomb component. This is the lid. It's got a little turbine here to spin the water. We've opted to use the Go Direct Vernier wide range temperature probe. It seems like it's a good fit. We've got the ignition source here, and there are two electrical plugs, one for the ignition source and one for the motor, so that we can spin the stir bar down there. All right, so the first thing we want to do, and I put notes on here, we want to add 2,000 grams of distilled water. So we now have a 10-pound balance. So you just want to make sure that you're using the one that says 10 pounds. There's a unit mode, so I just have it switched to grams. We'll put the water jacket on. It weighs about 810 grams. We can go ahead and zero that. And now we're going to add about 2,000 milliliters of distilled water. We're just going to keep going until the balance says 2,000 grams. I'm going to add the remainder using a distilled water bottle here. This gets calibrated using benzoic acid, so as long as we use the same firing conditions each and every time, the same conditions that we use for the benzoic acid standard, we should be able to use that calorimeter constant. So I do want to make sure it says exactly 2,000 grams. And right there we go, 2,000 grams. All right, so I'm going to transfer that into the bomb calorimeter. And at the bottom, you'll see that there are 3 legs sitting on the bottom, so that this can only be entered in one direction. So there's 2 indentations on this side, so that goes on the side that has the 2 pegs. It should sit in there very steady. All right, the next thing we want to do is load our sample into one of these little firing cups. Make sure it's nice and clean. You can see here that I've already done that. In this case, I'm going to be using some freeze-dried pineapple. So I've weighed that out on the analytical balance, and I have the exact mass for that. The next thing we have to do is use the ignition wire. This distance from one end of the card to the next is exactly 10 centimeters. So I just cut off a piece that's 10 centimeters. And then we're going to load it into these tiny little holes here, and then these little caps get pressed down so that it can't come undone. Same on this side. I lift up, push it down, so that that ignition wire is snug. The next thing we want to do is make sure the ignition wire is touching our sample, but we don't want it to be touching the cup. So it takes a little bit of finesse to get it where you need to. You can put a little bit of an indentation in the wire if you have to. So that again, the ignition wire should touch the sample, but we don't want it to be touching the edges of the cup. So that looks good right there. The next thing we're going to do is load. Sorry, I forgot this one step. We do have to add 1 milliliter of water to the bottom of the bomb. So I just use a micro pipette to soak up 1 milliliter of water. I've already injected that into the bottom of the bomb. Now we're going to carefully put this down in. Push down on it so it's snug, and then we're going to screw on the bomb lid. You want to keep going till it's snug. At this point we have to load the bomb with oxygen, so we're going to open this vent cap here. This is just a valve, so we're going to open that up. And you can see this is our oxygen tank. It's got a special adapter valve on it. It's got this very special end. This end is going to go on the middle peg here. It's got a little gasket seal, so we're going to push it all the way down. Now we want to very slowly open the oxygen valve. And what we're going to do is we're going to flush oxygen through this to get rid of any air that would be in the bomb. I'm going to let it go for about 30 seconds. The oxygen goes into the bomb, pushes out any nitrogen and old air that was in the bomb, so that we fully want a clean bomb with only oxygen. Alright, so now I'm going to turn it off. Now what I'm going to do is close the valve on the bomb, so now we can pressurize the bomb. This is where they say you don't want to put your head above this valve here because it's designed to withstand pressure, but if there would be a failure, rather than exploding the bomb, this valve is meant to blow and it's going to go straight up. So you don't want to have your head sitting above that valve. So same thing, now we're going to turn the oxygen on nice and slow, and we want to get it up to between I'd say up to 30 atmospheres of oxygen pressure. They say you shouldn't go over 40, so I try to stick as close to 30 as possible. If for some reason it does go above 40, you don't want to detonate the bomb, because that's going to create additional pressure and that could cause a major rupture. So nice little turns. You can see right now we're up to 5 atmospheres of oxygen, 10 atmospheres of oxygen, 15 atmospheres of oxygen, 20, 25, and we're getting pretty close to 30. So I'm going to go ahead and turn that off. It does drop a little bit. If I look down here, this is pretty close to 30 atmospheres of oxygen as well. It looks like it dropped a little bit below 30, so I'm just going to add a little bit more. So you can see it went just a little bit above 30. It looks like it's 30 on this valve. Now to take that valve off, we have to release the pressure. And now I can take this off and put the oxygen tank away. All right, so at this point, we're ready to load the bomb into the water tub. So rather than getting our hands wet, there's a little circle indentation on the bottom. We're gonna line that up with the center of the bomb here. So we're just gonna use these little tongs. There's little holes on the side to gently lower the bomb down in. And before we get our fingers wet, this is where we're gonna put in the ignition wires. It doesn't matter what side you do it on. So one ignition wire goes on the left. Push it down in there. And another ignition wire goes on the right. All right, so I'm gonna use the tongs to lower the bomb. You'll see some air bubbles coming up. But once that initial set of air bubbles disappears, you shouldn't see any new air bubbles hissing out of the bomb. If so, that means you would have a leak and would want to abort detonation. All right, so to review, I filled the bomb with 30 atmospheres of oxygen. I've got close to a 1 gram pineapple sample in there. The benzoic acid tablets are about 1 gram as well, so I kind of use that as my judge. We've got our 2,000 grams of distilled water. Now we're ready to put the propeller on. So it goes in this direction. And when you lower this, there's little pegs in there that won't allow this to spin, so that means it's in the correct direction. We have this rubber O-ring here that goes around the motor for the propeller and around this little flywheel. And then because it's plugged in, if I turn this on, that's going to start stirring the tub of water. Now to get this go direct, you could have this, if you're doing this as a demonstration with your class, you can have this connected to your computer. I'm just going to be using this little LabQuest 2 for today. So to get it connected, I just have to hit the Bluetooth button. All right, it should be blinking. On my screen here, I'm going to go to LabQuest app. It's already set up in time mode, so I'm going to change the settings to minutes. I don't think I'll need 45 minutes of data, but I don't want it to stop before I'm done, so I'm going to collect for 45 minutes. I'm going to collect 6 samples a minute, so every 10 seconds. That looks good to me, so okay. And now we need to get a baseline reading. So I'm going to hit collect. Actually, I need to go up to sensors and connect first. So wireless device setup, go direct. And if I look at the code on the back here, it says 1235. I'm not currently seeing that. So I'm gonna cancel, get out of here, try it again, sensors. Go direct. It's not picking up any sensors, so let me try this again. Oh, here it is. 101235. So I'm going to connect. I'll probably have to change the mode again. So back to minutes. I'm going to collect for 45 minutes just to be safe. 10 samples a minute. Okay. And now I'm going to start collecting data. So I'm going to let it sit here for 5 minutes to get a good baseline temperature because calorimetry is all based on changes in temperature. So I want a good baseline. And then we'll be ready to ignite. While that is going, we have these benzoic acid tablets here. So they're basically 1 gram. You would want to measure the exact mass of them. But if you'd want to show your students how to calibrate it, you would go through the same procedure. You'd weigh out the benzoic acid tablet. You'd follow the same exact procedure as we used here. And then I do have a spreadsheet that every time you ignite a sample, you're going to record that in the spreadsheet because after so many ignitions, there's some maintenance that needs done. Plus, if we have multiple benzoic acid sample calibrations, then we can use that as an average calibration standard so that if we know how much heat the benzoic acid tablet gave off, now we know how many kilojoules are released from an unknown sample per degree Celsius change in temperature. All right, so we'll wait a few more minutes here. At the end, you just want to wash everything down. I do have a towel here to dry everything out. We don't want to leave the water in the tub. To reuse that distilled water, we can just pour it back in a distilled water jug, but wipe everything down. If there shouldn't be any residual ashes in here, but I always like to give this a nice little clean out, wipe down. At the end of an experiment, there might be a little bit of ignition wire left. If you really want to get fancy, you can measure the length of those tiny little pieces. I haven't done that for any of the tests so far because I just don't need that many decimal places of accuracy. But you can line those up with this card, and for every length of wire left, if I have this much wire left, that would be the calories for the residual fuel wire. So if I have this much wire left, I would have to factor in 5 calories that weren't burned. So for every centimeter, it's 2.3 calories per centimeter. So we had 10 centimeters at the end. So that should be 23 calories per fuse. And that's why you can see there's a 23 here. But if I didn't use up that much, I could subtract those 5 calories. But again, I've never taken it to that level of detail to factor all that in. All right, so it looks like we're holding pretty steady at 22.6 degrees Celsius. We're at 3.5 minutes. We'll let it go another minute or two here. As far as the ignition buttons go, because we are using 10 centimeters of wire, we've got the common wire here, we've got the 10 centimeters, this all gets left connected. There's other bomb calorimeters that use 7 centimeters, but this should always be the common in 10 centimeters. It doesn't matter which wire goes on which side. And you can see the little sign here. When we get to 5 minutes of background data, we're going to push this for 5 seconds. You don't want to hold it any longer than that. Any less than that, it might not be a good ignition. And what you'll see, I don't know if the video will pick up on this very well, but for the first fraction of a second, you're going to see this turn red because there's a completed circuit. But in the rest of the 5 seconds, there's not going to be any light here, because what happens is the fuse gets so hot it burns out. That's the ignition source, and then everything should go up in flames inside the bomb, and then we should start seeing a temperature rise on our temperature probe. So we're at 5.3 minutes. We're at 22.6 degrees Celsius. So it looks like we are ready to go. So I'm going to turn the lights out so you can hopefully see this a little bit better. Maybe move to the shade here. Right there. And I'm simply going to press this button for 5 seconds. 1, 2, 3, 4, 5. So now we just sit back and watch. So this would be a good point in the lesson. Once you have it set up, maybe do a little 5 to 10 minute demo at the beginning of the period. This data can be collecting. You can see it's already up to 23 degrees Celsius. I would just let the data run in the background, let the data speak for itself. The students could move on to a new activity, and then periodically throughout the period, they would just record some data, make some observations, and then maybe wrap it up at the end of the class period with a class discussion about the data. So basically right now what we're looking for is a rise in temperature, but then it's going to start to level off, and then it might even start to cool down over time. So we're really looking for the change in the starting temperature and the highest average peak on the temperature curve at a maximum point. I usually like to find the maximum using the data analysis button, and then go a minute or two before that, a minute or two after that, and find an average peak temperature. And once you know that change in temperature, you would use the bomb calorimeter constant, because from the benzoic acid samples, we know how many kilojoules per degree Celsius it is. And then you would plug that into the data, or have the students do that, and they can calculate the kilojoules per gram of the burn sample. So for this experiment, this is the little card I was looking for. So I weighed out exactly 1.0234 grams of pineapple. So then at the end, once we know the kilojoules of the heat that the pineapple released, I'd divide by 1.0234, and that would give me the kilojoules per gram. So I just press the graph auto scale button. So it gives us a nice graph of the starting temperature, and you can see how the temperature is rising, and it should keep auto scaling as it keeps collecting data. All right, so at this point, I think we're gonna go ahead and stop the experiment. Normally we would press stop here if we're stopping before the 45 minutes. I was a little bit afraid of this. It looks like the battery on this died, so I probably should have recharged that, make sure it was all ready to go. But I think we're gonna get some pretty good data here, just because you can see that the temperature spiked, and then it pretty much started to go down a little bit and level off. So I think this will be our starting temperature. That'll be our highest temperature up there, and that should give us good enough data. All right, so now that the experiment's over, I want to show you how to take this all apart. So we do want to turn this motor off. Just take this little O-ring off. We can transfer the lid to this nice little stand that comes with it. At this point, we can take the ignition wires out. Just make sure you're grabbing by the stem and not the cord. We don't want to strip those. At this point, we can take the bomb out. Trying to pour off as much water as possible without spilling it in the jacket. I'm just going to set this off over to the side. At this point, I'm going to pour this distilled water into the big graduated cylinder over here. We could save that for later. Rebottle it later. And we just want to give this a nice wipe down. This stainless steel, we don't want it to corrode. That's one reason we want to use distilled water, so that there's not all those minerals in it. That back in here. And then with our bomb over here, we want to slowly release the pressure. So we'll open this little valve. I'm going to give the outside of the bomb a good wipe down. All right, that sounds good. So I should be able to safely take the lid off. You can see there's that little bit of moisture in the bottom there. That's probably the milliliter of water we originally put in there, plus any extra moisture that was created by the combustion. I'm just going to go ahead and give that a good wipe down. There is a procedure if you really want to get technical and you really want all the decimal places of your data, where you would wash that out, you would titrate it. I think looking for nitric acid and some other components, because then you can factor those into correction factors. But I figure at a high school setting, just calculating the kilojoules per gram of a fuel source is probably good enough. I'm going to zoom in here on our combustion cup. If I lift up these little clips, you can see there's a little bit of unburned ignition wire. It actually looks like a little pellet. That's just from the wire getting super hot. Again, if we really wanted to factor in every single variable that could change our data, we could either measure the length of this wire, or in that case, maybe weigh the wire. But again, I'm just looking for an approximate heat kilojoules per gram of fuel source, so I'm not going to take the time to measure that tiny little piece there. Or on this side, this tiny little piece. All right, so hopefully that gives you a pretty good idea how to get this to work. If at any point you have any questions, just let me know. If you do go with this setup, the nice thing about putting it on your computer, then you'll have the data directly on your computer. In this case, I just need to save the data. So go up to File, Save. It's going to go on my USB. I'm going to type pineapple, actually freeze-dried. Pineapple. I tried it once with just regular fresh pineapple, and the moisture content might have been too high to actually get a good ignition. I thought pretty much anything would burn in there, no matter how moist it was. It could have just been a bad firing. When I opened up the container, I could still see pretty much all of the fuse wire, so it might have just been a misfire. That's happened maybe 2 or 3 times in doing this. So again, if you're not getting the data that you're expecting, open up the bomb, and it could just be a simple misfire, so you would just clean it out and collect new data. That's happened every once in a while. So I'm going to save it. And then I'll just plug that USB into my computer, open up graphical analysis, and then I should have all my graphing data here.